Welcome to the third lecture on electromagnetic fields and waves. Today we will continue with the review of basic mathematical tools, and we will specifically deal with integral calculus and divergence theorem. Let's start with the concept of line integrals. The line integral L.dl integration over L is the integral of the tangential component of A along curve L. By a line, we mean the path along a curve in space. We shall use terms such as line, curve, and contour interchangeably. So the line integral A.dl can equally be represented by the following forms, which all are equivalent. If the path of integration is a closed curve, such as A, B, C, A, shown in the figure here, the line integral becomes a closed contour integral, as you see in the notation of the integration sign here. The line integral is the integral of the tangential component of A, vector A, along the curve L. It requires L to be a smooth and a continuous curve. The vector A may be a vector field component. Here we should make a note. Line integrals are said to be path independent if the solution of the tangential component of the vector A is independent to the path L taken within the field. The most common example of path-independent integrals used are work energy solutions, integrating the force over the path length L. Path independence of vector A occurs if curve of A is equal to 0. Here is again notation for the line integral. A.dl in closed integration represents for a contour of length L, gives the circulation of vector A around the contour L. Let's discuss a specific example. Given the following equation for f, find the line integral of f along the following paths between points 0, 0 and 2, 1. The first path is a straight line represented by the equation y is equal to 1 over 2x. If we integrate dy, this is what we find. If I write the equation f.dr, it takes the following form, and the final integration is equal to 1. Let's consider a second case of computing this integral along a parabola given by this equation. If we do that, we find an answer 2 over 3. Let's discuss now surface integrals. Given a vector field A continues in a region containing the smooth surface S, we define the surface integral of the flux of vector A through S as follows. A dot ds over surface S can be written in the following form, and all of these three representations are equivalent. Here you see a vector field A in the figure, a surface S, and vector AN here is normal to that surface. ds is given in the following form, and if we have a closed surface, then the integration has the following notation, and it gives us the net outward flux of vector A from surface S. Let's work out a simple example and try to calculate the area of a circle of radius r. Surface integrals are actually double integrals that calculate the area of a closed surface. So integration of ds in circle coordinates is of the following form, where rho varies between 0 and 2 pi and r varies from 0 to r. If you carry out the integration with these limits, the result is p r squared, the familiar result for surface of a circle. Let's now discuss the volume integrals. Volume integrals are triple integrals that calculate the volume of an enclosed surface. The volume differential is integrated in appropriate coordinate system. Here is the representation of volume integrals. They are both equivalent. Rho v here is a volumetric density function. Let's again work out a simple example and try to calculate a volume of a simple sphere with radius large r. We write the integration in cylindrical coordinate system. This is the dv element. R varies from 0 to r, theta from 0 to pi, and phi from 0 to 2 pi. If you carry out the integration, the result is 4 over 3 pi r cubed. This is the familiar result of a volume of a sphere. Our next subject is the del operator. The del operator is written in the following form, and it represents a vector differential operation. In Cartesian coordinates, the del operator has the following form. In cylindrical coordinates, this is the form of the del operator. And finally, in spherical coordinates, the del operator an ordinary vector A can multiply in three different ways. The first one is a multiplication by a scalar A. The second one is multiply another vector B via a dot product, written as A dot B. The third one is multiplication with another vector via the cross product, A cross B. Now let's have a look into the del operator. We have three different ways that the operator del can act. It can act on a scalar function, so del t. This action has a specific name called as gradient. The del operator can act on a vector function v via a dot product. We call this specific operation as divergence. And the third type of a product of the del operator with a vector function v is through a cross product del cross v. We call this operation as the curl. Finally, the Laplacian of a scalar is written as del square t. So this, as I already told you, is called as the Laplacian. Let's have a closer look into these operations. The first operation of del acting on a scalar function is called as the gradient. The interpretation of this operation is as follows. The maximum space rate of increase of the scalar in a specific direction vector. So its magnitude gives you the slope or rate of increase along this maximal direction. It's written as divergence, gradient v, and the result is a vectorial quantity, the space rate of increase of v in the direction an is equal to the projection of this vector. The second type of operation of the del operator we called as the divergence. Definition of the divergence is the net outward flux of A per unit volume as the volume about the point tends to zero. If you write this down in terms of equation, this is actually what it represents. If you write it down in a coordinate independent form, this is the relation. Let's have a look in the geometrical meaning of this. The net outward flux of A per unit volume as the volume about the point tends to zero. Let's have a look into these figures. Divergence of a vector field at point P. In first case, it represents a positive divergence. In the second case, in figure B, we have a negative divergence. And finally, the divergence is zero at figure C. In this slide, you see representation of the divergence of vector A in three different coordinate systems. The first one in Cartesian, the second in cylindrical, and finally the third in spherical coordinate systems. Let's discuss basic properties of divergence. Divergence produces a scalar field. Divergence of a scalar function s, that is del dot s, is not defined. It makes no sense. The divergence is distributive and it can be applied also in the form of equation 4. The divergence theorem states that the total outward flux of a vector field A through the closed surface S is the same as the volume integral of the divergence of A. In other words, writing this mathematically, this is the divergence theorem. A third type of operation of the del operator on a vector function v is the curl operation. The curl of a vector field A is a vector whose magnitude is the maximum net circulation of A per unit area. as the area tends to 0 and whose direction is the normal direction of the area when the area is oriented to make the net circulation maximum. If we put this definition into mathematical language, this is the form of the equation of the definition of the curl. In Cartesian coordinates, curl of a vector A can be written using this equation, and component-wise this is the form of the curl operation. Properties of the curl. The curl of a vector field is another vector field. The curl of a scalar or curl S is not defined. It makes no sense. Curl of A plus B can be distributed in the following manner. Curl of scalar multiplied by vector A can be written using this relation. And finally, divergence of a curl of vector A is equal to 0 and curl of a gradient S is equal to 0. Let's have a closer look into the geometrical interpretation of the curl. Curl of vector A is a measure of how much the vector A curls around the point in question. The functions in the figure below have a substantial curl pointing in the z direction, as the natural right-hand rule would suggest. Let's now discuss the fundamental theorem of curls, that is, the Stokes theorem. The Stokes theorem states that the circulation of a vector field A along a closed path L is equal to the surface integral of the curl of vector A over an open surface S bounded by L. See the figure below. Provided that the vector A and curl of A are continuous on that surface S. This is the end of our lecture number 3. See you next time.